Okay, and so I'm going to go ahead and talk as if we're just lecturing in class. Okay, so again, in this chapter, okay, class at 6 was recorded BFG. So it does take, this lecture will probably take about 20 to 30 minutes, and it takes, after I'm done, it takes about another 20 to 30 minutes for it to actually convert to an MP4. So it will definitely be ready maybe around 6:30 or 7. All right. But again, if you have to leave, just feel free to chime in and out. And if you have to just go, it's not a problem. I'll continue recording the lecture. Right. Okay, so we talked about source transformation and the other recording. And source transformation, again, is a technique for simplifying circuits. Now, what we do with those is we actually transform a circuit into something called either a Thevenin equivalent or Norton equivalent. And we use these to simplify circuits. And once we simplify the circuit, we can actually put any load we want on that simplified model, and then we can actually predict what's going to happen if we put a different type of load on that model. And so it just makes it really easy to calculate loads and how things are going to work. And imagine if we didn't do that, if we had a very complex network circuit, and every time we put a different load, we'd have to go through the entire calculations all over again to figure out what the result is on that load. But Thevenin and Norton equivalents allow us to actually simplify our main circuit so that we can put different loads on there and see what happens. So again, circuit simplification technique, and can be applied to any circuit consisting of resistors and sources. So if you look to the left, we have a resistive network containing independent and dependent sources. And when you see there A and B, that's where you physically would connect a load. So it could be a resistor, it could be a fan, a motor, it doesn't matter what it is, but it could be anything that you're going to be supplying power to. Right? And again, that's just a black box theory. What's actually inside what's called a Thevenin equivalent would be a Thevenin voltage and a resistive Thevenin resistance. And again, when we talked about source transformation, if you haven't seen that yet, go ahead and watch that video and then come back to this one. But we simplify circuits to give us a voltage and a resistor in series. And by the way, this is a question on your certification exam for what's called Certified Biomedical Equipment Technology. So you're always going to get asked a question on Thevenin or Norton equivalent, and you basically just need to know how to recognize them. Okay, so again, what instrument, this goes back to your lab, what instrument could we use to determine the voltage across and the open circuit in these two circuits? Of course, the one to the left is just that black box theory, and then of course the one to the right is our Thevenin equivalent voltage with the Thevenin voltage and Thevenin resistance. And of course we know when we are measuring voltage, we use a voltmeter. Now what we have in class are digital multimeters. So multimeter meaning they can measure resistance, current, and volts. So had you said a multimeter, that would have been fine, but you would just make sure you know that you're on the voltage setting. And if we're not on the right settings on our meters, we know already that we can blow fuses on our meters. Okay. What instrument could we use to determine the current through a short circuit between nodes A and B in these two circuits? And again, when we're measuring current, we know that the proper tool would be an ammeter because we're measuring amps. And again, with your digital multimeter, you have to make sure you're in the correct setting for measuring amps, or we blow fuses. Okay. And the next one, this is a very simple, intuitive question because it's labeled in a diagram. Is if we create a short circuit at the output between the nodes A and B, what is the current in this? What is the current in this short circuit? So what it's asking, and I'll draw a line here in red. So if I were to actually put a piece of wire across A and B and short the output, what is this circuit equivalent to? So I have a voltage source and a resistor, and I have a path all the way back to ground, and I'll do that with a pencil. And so imagine that we have current going this way, down that short, back here, and that way. And so if I want to find out what the current is in that loop, it's V is equal to I times R. Again, algebraic manipulation. We know that I is equal to voltage over resistance. And the voltage and resistance is our Thevenin voltage and our Thevenin resistance. So meaning A would be the right answer in this case. And let's go ahead and talk about simplifying circuits again. So here we have a circuit, and the author is asking us to find the Thevenin equivalent of the circuit below to the left of the terminals A and B. And of course, A, in case it's hard to see, is right there, and B is right here. Now we're looking for the Thevenin equivalent, so that means that I'm looking for something that has a voltage source, my great drawing skills, that is in series with a resistor, a Thevenin resistance. Right. There we go. And so we have a technique for doing this. Right? So if we wanted to find the open circuit voltage by looking at this circuit, and this is one way we're going to do this, we can do these mesh analysis and draw current loops through these circuits, which I have done here. We have loop 1, and we have this other loop right here, right? And we want to find this open voltage right here. In other words, an open circuit voltage, meaning we have nothing tied to the load over here. There's nothing hooked up here, and we call that open circuit voltage. And if we do that, we can actually go through the mesh analysis, write our equations, just like we do with regular mesh analysis. You see here we have 2 loops, we have 2 equations, and then we can do some distribution and go ahead and solve for the open circuit voltage. Now again, this is a very simple circuit. Now here's another way of doing this. And again, when we're looking at something with just a few elements, it may not seem like that big of a deal between going from the regular mesh analysis or using something like Thevenin's equivalent, because there aren't that many extra steps in either one. But imagine that this is a much larger circuit, and the more complicated the circuit gets, you're going to see that using Thevenin equivalent and Norton equivalents, using what's called source transformation techniques, will actually help you simplify that circuit very, very quickly. Okay, so this one says find the short circuit current, and this is part of the first step. And it says here we use current division, noting that the short circuit effectively removes a 12 ohm resistor from the circuit. So in this particular case, and it's not always going to be like this, if we had a 12, in this case any resistor, in this case it's 12 ohms, and if we had that resistor in parallel with this open circuit, and then we short it, and so what they're doing here is step 1 is to go ahead and create a short across that, because that's our first step. Like that. What ends up happening is, and you can practice this in the lab, if I were to put a piece of wire at one node and across the other node, across a resistor, I've effectively removed this resistor. So this resistor here doesn't exist electrically anymore, because current wants to take the path of least resistance. And so what's going to happen is that current is going to come this way, and it's got a decision to make right here. You can either go down the 12 ohm resistor, which is a lot of work, or it can say, hey, I'm going to go down this way because I got a short and there's nothing over here, and bypass that 12 ohm resistor. It's just much easier. And so effectively the current's not going to go down across the 12 ohms, so there won't be any voltage drop across that 12 ohm resistor. So for analysis, we can sort of just ignore that 12 ohm resistor because we're not going to have any current going through it if we short out the output. So what are we left with? We are left with a 2 ohm resistor. Let me go ahead and erase this because I got a lot of mess here. So now, if we remove this, and I'll do this in red, if we remove this, and we're left with this component and this component, realize that now these two components are in series together. Oops, dang it. Sorry, my mouse is... And so we have 2 resistors in series, which is 10 and 2. We can go ahead and add those up together, and that gives me 12 ohms. And now remember that we have a node over here, an essential node and another essential node. And so now I have this 8 ohm resistor in parallel with this combination of the 2 and the 10. By just simply using this technique of shorting the output, thereby eliminating the 12 ohm resistor. And Give me 1 second. And so when we do that, we can actually use the parallel resistance formula to get the equivalent resistance. Excuse me. And then when we got the 8 ohm resistor in parallel with this 12 ohm resistance, we get this equivalent resistance of 6 ohms. And no, we haven't done the whole thing yet. So basically what I've done is, and I'll see if I can redraw it right here. We have that current source, and we've done that equivalent resistance. I know this is not the greatest drawing. So I've now simplified that circuit, and basically you can do a lot of this in your head. This is going to be a, what do we say this was? A 6 ohm resistance. And we're given the current to be 15 amps. And so now that we have this current source in parallel with this 6 ohm resistor, we can go ahead and do a source transformation and get this circuit right here. So hopefully that makes sense. Any questions so far? Nope, good. Okay, and if you don't know how to do source transformations, make sure you go back to the source transformation recording. And so it says we could use an ohm meter to measure the Thevenin resistance so long as there are no dependent sources in the circuit, and we remember to kill the source by setting its value to 0. Okay, so this is another thing that we have to learn. If we are going to use a dependent source in the circuit, because it's a constraint, we have to actually just eliminate it. And so basically, if you get your multimeter and you put your multimeter right across A and B, you can literally measure what the Thevenin resistance is. And you'll do this in lab. You'll calculate it, and then you'll actually measure at the output without any load. Remember, we're not hooking up the circuit to any output, and you should be able to actually measure current going through there, and you can actually measure the Thevenin resistance. Okay, we are on slide 8. And let's do this one. Find the Thevenin resistance. And I think the author meant to say by killing the source and making series and parallel combinations of resistors. Okay, so here's another way of doing this. We have a current source here. We have that same resistive network, and we have A and B as the open circuit voltage. Right? Right. So it says find the Thevenin resistance. And so this is just a way of finding Thevenin resistance. So what we do is we just go ahead and kill that load. We don't care what that is right now. And now we just have this parallel network. And so what we're doing is, if I were to hook up the meter to that circuit, what would the ohms read? What would you actually read in the meter? Of course, with whatever tolerances we have, and we can actually calculate that. So if we have this 8 ohm, 2 ohm, 10 ohm, and 12 ohm network, what do we have here? We got this 12 ohm resistor, which is right across the leads of the meter, and then that is in parallel with what? If we look at it from just this, it's in parallel with, try to do this in a different color. So this 12 ohm, if I look at this essential node and this node here, we can see that the 2 ohm resistance is in parallel with the 8 ohm resistor, which is in parallel with the series, excuse me. The 2 ohm resistor is in parallel, let me redo that again, I did it again. 2 ohm resistor is in series with the 8 ohm resistor, which is in series with the 10 ohm resistor. So these 3 resistors are in series, but all 3 of them are in parallel with this 12 ohm resistor. So we can use the parallel equation to find the Thevenin resistance, which is this thing here. And in this case, we get 7.5 ohms. So let's see, what do we got here? 5:43. Okay, we still got time. An alternative approach, find the Thevenin equivalent of the circuit to the left of the terminals A and B using a series of source transformations. So let's go ahead and do source transformation now, instead of doing the resistive parallel series network combination. So I'm going to go through this kind of quick, because we should know how to do source transformations. And again, if you don't, go review that video. And so here we recognize something. I have a current source that's in parallel with a resistor. And we know that we can actually do the source transformation and turn that into a voltage source in series with that same resistor, the 8 ohm resistor. And so again, just a little quick review on the math. If I have 15 amps divided times 8 ohms, that'll give me the voltage across this network, which is 120 volts. And that will be the value of the voltage source that we put in its place. So then we redraw the circuit. We'll redraw it with a voltage source. And we keep that same ohm resistor because that was part of our initial calculation. So now we've turned what we have right up here on top, the 15 amp with the 8 ohm in parallel. We've converted it to a voltage source, 120 volts, with an 8 ohm in series. Now again, this is just for analysis. This technique is only to help you simplify the circuit. You're not physically going to do this on your circuit. It's just a quick way for you to look at it, do some quick analysis to simplify it until you can actually have something you can work with, like in a simple calculator. So what do we have now? We have this 8 ohm resistor that's in series with this 2 ohm resistor. So now we can see, and it's actually in series with this 10 ohm resistor as well, because if you think about it, all of this is in series, and it's in parallel with this 12 ohm resistor, which is the open voltage circuit. So let's go ahead and see next what's going to happen. And they even tell you right here, 2 ohms plus 8 ohms plus 10 ohms is going to give you 20 ohms. They already calculated the equivalent resistance to the left. So as you can see, they've done that with the 20 ohm resistor, which is what we have here. And we skipped a step here. So they have the voltage source with the 20 ohm resistor in series. And they kind of skipped a step here for you, but let me go ahead and fill in that gap. All right. So what they did was, and I'm only going to do that little piece, where they had the 20 ohm resistor in series with the voltage source in series with it, and we had this circuit here. I think it's this one, right? And so we have this network right here, and I'm going to change the color so I can show you. Remember we said we have a voltage source and a resistor in series. We can actually convert that to a current source and the same resistor in parallel. So what we did is we changed, this is a step they actually left out, the author left out. So they changed that into this right here. And let me do that in the same color. Oops, I meant to do a box. And so this 20 ohm resistor with that current source is equivalent to this voltage with this resistor in series. Again, the way to do that, we still use Ohm's law. So if we had that resistor being 20 ohms times 120 volts divided by the 20 ohms, we would get 6 amps. And so our current source would be 6 amps. And so now we've simplified this circuit into what you see right here. Okay. We have a current source with a resistor 20 ohms in parallel and a 12 ohm resistor in parallel. So now we can go ahead and take that equivalent combination of 20 and 12 in parallel, and they've already done that for us, and they've calculated it to be 7.5 ohms right down here, and that is our equivalent resistance. We have, and again, the step the author is leaving out would be the current source that is in parallel. I'm almost done here. Hopefully I'll get done before your class starts. And we said that was 7.5 ohms at 6 amps. Okay, and then we still have point A and point B. But we're asked to find the Thevenin equivalent. So we know that this is what's called the Norton equivalent. This is Norton. And over here we have Thevenin. And so in order to go from a Norton to a Thevenin, we just do one more source transformation. So we use a 6 amp that's in parallel with the 7.5 ohms. And we go ahead and calculate the voltage drop, 6 amps times 7.5 volts, which they've done for you right here. And that'll give us the value of what the voltage source should be, which is 45 volts. And then we can go 45 volts in series with a 7.5 ohm resistor. And this circuit, the very bottom, would be our Thevenin equivalent. And so now, if I wanted to put any kind of load, let's say I'm testing motors, and I want to put a bunch of different motors with different inductance, which is different impedance, which is a different type of resistance, I can just go ahead and calculate this simple voltage resistor combination and how it will affect any load, instead of trying to go back to that original circuit and try to recalculate everything every single time I change the load. Okay. So it's a design trick. Next question. The Norton equivalent is just a source transform of the Thevenin equivalent. Therefore, it says this voltage Thevenin with a resistance Thevenin in series is equivalent to a Norton current with a resistance Thevenin in parallel. And it says the answers are Norton current is equal to V Thevenin over R Thevenin. It says voltage Thevenin is equal to resistance Thevenin times Norton current. Neither A or B are both A and B. And we know that both A and B are correct, which is actually answer D. Okay. And this is the last slide. And so it says, now find the Norton equivalent. So we're going to do basically the same thing we did before. Find the Norton equivalent of the circuit to the left of terminals A and B. All it's saying is find, what's left of this point A and B, and find this Norton equivalent. And it says, just use source transform. So just the source transform of the Thevenin equivalent. If we get all the way down to which we did before, actually this is a different circuit, different values, isn't it? So we can go from here to there, Norton. So if you do the simplification, you're going to end up with a Thevenin equivalent prior, right before you have to do the source transformation and get to a Norton equivalent. I'll put a big N here. And that's it. These are source transformations. They're only used to simplify circuits for analysis purposes. You don't physically actually change your circuit or your design every single time. The reason we have a lot of those components could be that we need to draw current from one of those other loops for some other part of a circuit. Or, again, this actually could be used to simplify a circuit. If you had a very complex circuit and you only had one output A and B, and let's say the 2 ohm resistor or the 10 ohm, or those weren't significant for any other load, then yeah, you could probably simplify the entire circuit just down to 2 components. And if you did that, you'd save a lot of money in design. So it is possible. I mean, that is a valid reason, but for the most part, it's used for design because you're varying loads. So between A and B right here, you're looking at how this circuit affects many different loads, and it's easier to test this little circuit here with 2 components versus the top circuit up here with multiple elements. And that's it. So I hope you enjoyed this lecture, and I'll go ahead and put another one on maximum power transfer, but hopefully these will get you ready for the labs on Thevenin and Norton equivalents starting next week. So have a good evening.